Hello, my name is Tunai, and the title of our work is Detecting Marine Species in Echograms via Traditional, Hybrid, and Deep Learning Frameworks. Marine biologists and acousticians have been using acoustic monitoring techniques to study underwater environments because of its non-invasive and thorough characteristics. Data coming from echo sounders such as ASL's AZFP can be interpreted in images called echograms, where the x-axis represents time and the y-axis represents the depth in the water column. The manual or semi-automatic interpretation of such echograms can be time-consuming and prone to inter-expert disagreements or errors. Therefore, what we try to do in this work is to perform a comparison between machine learning-based approaches for the automatic detection of marine species in such echograms, in particular schools of herring. In this work, we use data collected with AZFP instruments in 4 different frequencies because it provides complementary information with respect to the presence of schools of herring. In order to effectively explore the machine learning-based solution space, we test 3 different approaches. The handcrafted one, that's the most commonly observed in the related literature, where we use our custom region of interest extractor and then extract 4 handcrafted features that drive a classification task with a support vector machine. The second one, called hybrid, where we again use our custom ROI extractor, but this time we do the classification using custom trained convolutional neural networks. In the third one, the end-to-end approach, we used object detectors to do both the localization and classification of candidates of schools of herring. This diagram shows the computational pipeline of the 3 frameworks, of the 3 approaches, and we are going to discuss it in more detail, starting with the ROI extractor. In our custom ROI extractor, we use echograms coming from 4 different frequencies, and we start by denoising them with a median filter in the x-axis, therefore the time direction. We then create binary images by applying an adaptive thresholding task, and we further filter it with morphological operations of opening and closing. We then put these 4 binary images together and only keep positions of values higher than 2, therefore positions where we found acoustic response in more than 2 frequencies. We further filter these results based on the size of these sets of connected components and create bounding boxes that are filtered based on their orientation with respect to the horizontal axis. The output of our ROI extractor are bounding boxes where there's a high likelihood of the presence of schools of herring. We use these bounding boxes in the first 2 approaches, starting with the handcrafted one. For each bounding box, we are going to calculate 4 handcrafted features that are specific to schools of herring: the mean intensity of the content of a certain bounding box, the ratio between its major and minor axis, eccentricity, and circularity. These 4 features are going to drive a custom trained SVM classifier, which is going to classify each bounding box as herring or background. Similarly, we are going to use these bounding boxes generated by the ROI extractor with approach number 2, the hybrid one. But this time, we calculate the visual features using custom-trained convolutional neural networks. But the result is once again a binary classification task. When first working with the end-to-end approach, we noticed a severe limitation related to the scale of the objects we were annotating. When downsampling the image to match the input requirements of feature extraction networks, these objects would effectively disappear at a certain point in this network because they were represented by less than a pixel in a feature map. In order to overcome this limitation, we proposed the tiling strategy, where we break the image down into tiles of a fixed size that does not require resizing in the beginning of feature extraction networks. We then annotate the image, break it down into overlapping tiles, and use these tiles for the training process. During inference, we break the input image down into tiles, perform individual detection in these tiles, and finally concatenate the detection for the final detection output. We manually annotate 358 echograms that were captured using an AZFP instrument deployed by the Department of Fisheries and Oceans. We then divide this dataset into 80% for training and validation and 20% for testing. Qualitative analysis showed that all three methods do very well for easier to identify schools, while in more challenging scenarios, the handcrafted approach missed most of the schools. When considering the whole test set and intersection over union thresholds of 0.3 and 0.5, the overall best performing method for the lower threshold was the hybrid approach with Inception v3. For the higher threshold, the best performing method was the end-to-end approach with YOLO v2. In this work, we compared three machine learning-based approaches for the identification of marine life in echograms. We also proposed a new ROI extractor, tiling strategy, and dataset of echograms. Even though hybrid approaches and end-to-end approaches did extremely well in our experiments, we recommend the use of the end-to-end approach because it doesn't use features that are specific to schools of herring. Thank you.